Welcome to On-Screen Learning. Wolff's Law. The Wolff's Law, developed in the 19th century by the German anatomist and surgeon Julius Wolff, 1836 to 1902, states that bone will adapt to the loads under which it is put in a healthy person or animal. If loading on a specific bone increases, the bone will remodel itself over time to become stronger to resist that form of loading. Trabeculæ's internal architecture undergoes adaptive modifications, followed by secondary improvements to the external cortical portion of the bone, which can become thicker as a result. The opposite is also true. If the load on a bone decreases because of the lack of stimuli needed for continued remodeling, the bone will become less dense and weaker. This decrease in bone density, osteopenia, is known as stress shielding and may occur as a result of the replacement of the hip or other prostheses. By being put on a prosthetic implant, the usual stress on a bone is shielded from that bone. Mechanotransduction. In response to loading, bone remodeling is done by mechanotransduction, a mechanism by which forces or other mechanical signals are transformed into cellular signaling biochemical signals. Mechanotransduction leading to bone remodeling requires the steps of mechanocoupling, biochemical coupling, the transmission of signals, and cell response. The particular effects on the structure of the bone depend on the length, severity, and loading rate, and it has been found that bone formation can be caused only by cyclic loading. When filled, fluid flows away from high compressive loading areas in the bone matrix. Osteocytes are the bone's most abundant cells and are also the most susceptible to mechanical loading caused by such fluid movement. By signaling to other cells with signaling molecules or direct touch, osteocytes control bone remodeling after sensing a load. Osteoprogenitor cells, which can differentiate into osteoblasts or osteoclasts, are also mechanosensory and will differ depending on the loading situation. Computational models suggest that mechanical feedback loops can stably control bone remodeling by reorienting trabeculae in the direction of the mechanical load. Examples: tennis players' racket-holding arm bones become more robust than those of the other arm. Their bodies have reinforced the bones of their racket-holding arm as it is regularly put under higher than usual pressures. During the serving, the most critical loads occur on the arms of a tennis player. There are 4 major phases of a tennis serve, and during external shoulder rotation and ball impact, the highest loads occur. A twisted bone density profile results from the combination of elevated load and arm rotation. In addition to their exercise, weightlifters also show changes in bone density. The deforming effects of torticollis in children on craniofacial development. Astronauts also suffer from the reverse. They appear to lose bone density in a microgravity environment.